Hey guys, looking sharp, looking good. You had your showcase today?
Yeah. Pretty neat. Even though it wasn't like much people from the industries.
I think it's tough right now with COVID and everything. I think people are still figuring stuff out.
You insert the hole. You insert the hole from one end. Why on God's earth would you fucking define a hole middle of the part? How would you have any idea what the hole size is? You have to use calculations. That's so stupid. They should do this with the side. Additional sections. Yeah. So it's 13 in the middle, which means we need to go back and figure out what whole side on the end is going to give us a 13 diameter in the middle. And then we're going to have to go back and update the center. Yeah, I know, but I don't know. I have to do it not for the food. I keep it.
Hey Chris. Yeah, back's getting better, getting a little better every day. Yeah, just to make sure to stretch into ice every day. I'm hoping it's better by this weekend because I'm seeing my mom this weekend and I don't want her to worry about my back. So I want to make sure it's better before seeing my mom. I did not. I wanted to go to the showcase after lunch today, but something came up, and then I had to go back to my office, so I didn't get a chance to go. But I heard it was great. I heard. All right, it's 5:30, so let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, good. Yeah, I heard the showcase was today. I heard it was great. Yeah, unfortunately, I couldn't make it. And I was originally going to go after I had lunch with Dr. Sanders today, but something came up and I had to go back to my office. And by the time I was done with that, the showcase was over. So, but I heard it was wonderful, and and congratulations to everyone who did great today. Okay, so so I graded your midterm. So I actually graded them yesterday, but I didn't want to get any emails over the weekend, so I waited until this morning to post it. And so you should see your scores on Canvas, right? And if you're here today, I have the exam, so you can pick them up after the lecture. And so you might have noticed something interesting, because the exam was 50 points, right? So but for the first time ever, ever since I started working here, I decided to curve the exam, because as I was grading it, what I was seeing was that, especially for the later questions, a lot of it was kind of rushed. And so, just judging just based on what everyone was working on, I felt like the exam was about half a question too long. And so I cut about half a question's worth of points from the exam. And so the exam is worth 45 out of 45 instead of 50. And so the score that you got, just take your score, divide by 45, and that's going to be your score on the exam. And so with that, the average was about 82%. And so it's about 36.7 out of 45. So that's about 82, which is good, which is a very healthy average. So, I could tell that, you guys were prepared for the exam. You guys knew what you were doing. It was just kind of a few too many things to do. And so, I think if I had to revise the exam again, I would probably take off some of the, like I asked you to write equations for a little bit too many nodes and cells. And so I might have taken off 2 or 3 or 4 of them, and I think would have been a bit more reasonable. But but overall, it was good. So that kind of explains kind of the scores for that. Okay. Okay. And so with that, we are launching into our last set of lecture notes here. Okay. And so that's going to be our finite volume equation unsteadiness, right? So I think we started it last week before or I guess after the midterm. We did it on Wednesday, and then we'll probably take the rest of the week to finish that up. And remember, the plan for next week is that I want to have just time in class for you guys to work on the project, okay? Because the project, it's a fair amount of coding. It's also, there's a fair amount that you're gonna have to work out by hand as well. Remember I talked about last week, like you have to combine higher order schemes with time marching. That's something that we're not going to do in the class, but you guys should be able to work it out, based on everything we've learned. And so I want to make sure I have time in class, when everyone's together, when I'm here to help to kind of work those things out for you. Okay. And so I know for this class, generally a lot of you like to attend virtually, which is fine. But I think next week, if you want to kind of take advantage of the time that you have, with me to work on your final project, it would be a little bit more effective if you came in person. Okay. I'll still come to the computer every now and then just to check questions on Zoom, but it's just a lot easier for me to kind of work with people in the class, and people kind of physically here raising their hand kind of naturally catches my attention a lot more than on Zoom. And so if you want to work with me on your final project next week, you want to make sure you come to class.
So next week we don't have lecture, we just working on the.
Exactly. Yeah. Yeah, and I think with based on how far we got last week, we might end early on Wednesday as well. And so basically any extra lecture time we have after finishing these lecture notes will be just going towards the project. Yeah, and so of course if you need that extra time to work on other stuff too, that's fine too. I'm your professor, I'm not your mom, and so you guys can spend the time how you want. But if you do feel like you need the feedback from me, I think that's a good time to do it. But of course, you can always come to office hours. You can always email me. We can set up appointments as well. I just thought the class time would be useful just because we're all together, so you can kind of debug stuff with your friends while they're here, or just kind of get some one-on-one time with me, in front of the computer. Okay. All right, so that's the plan for the rest of the class, rest of the semester. So are there any questions I can answer before we get started today? Okay, all right, so let's go ahead and continue. So our last topic that we started last Wednesday was time marching schemes for finite volumes. Okay. All right, so this is kind of the last thing that we're going to do, right? And so we've kind of followed the same trajectory or same path as we did for finite differences, right? And so first thing we covered was diffusion, right? We did 1D, 2D. Next thing we did was convection, and then the last thing that we do is time marching, right? And so we kind of arrived at the same place. And thankfully, there's not really too much new here, right? The only addition is that now we have the time derivative term to worry about. Right, so now our finite volume equations are going to have this partial phi partial t, right? But in true finite volume fashion, we're going to be integrating these terms. Okay. Thankfully, there's really not much, or there's really nothing really special that we have to do here. Okay, because we're kind of blessed with the fact that we're taking an integral in space. Here I have the 1D version, which is just an integral x, but I'll show you the 2D version in a second. But our derivative here is in time, okay? And so these two actually don't really interact with each other. And so what we can do to perform this integral is that we just directly apply the trapezoidal rule. And so remember, the trapezoidal rule, the way that works is that we take our integral, we evaluate the integrand at the centroid, okay? And so in our case, that's going to be at C being the centroid of the cell, and then we multiply by the length or the size of the cell. Okay? And so in one dimension, the size of the cell is just going to be delta x. Okay. Right, so that delta x just comes directly from the integral. And then from here, we can just apply our usual forward difference for the time derivative. Okay. Okay. And so what we get in the end is that partial phi partial t becomes phi n plus 1 minus phi n all divided by delta t. Okay. This is multiplied by delta x. And since we're applying this this quantity at the centroid, these are just phi sub c's, okay? And so this integral right here, through our finite volume manipulations, becomes that, okay? And then we're just going to plug this in with the rest of the equation and then evaluate it as normal, okay? Of course, it's going to depend on whether we have an explicit scheme or implicit, but we'll kind of cross that bridge when we get there. Okay? And so this is the 1D case, right? And so our first example today is going to be 1D, but of course in 2 dimensions, then we have our double integral, right? And so in 2 dimensions, we have double integral, partial phi partial t, dx dy, right? And so if we apply the same process as we did before, then this is simply phi c n plus 1 minus phi sub c at n all divided by delta t multiplied by delta x delta y. Okay. And so this right here is the 2D version. Okay, so we'll get to that kind of later on in the class. Okay. And so that's what we're going to do with the time derivative term. But of course, we have all of our diffusion and convection terms as well. Okay. But for those, we're just going to treat them as normal. Okay, so we're going to treat those again as normal. And so, in 2 dimensions, that means we're going to get our 4 integrals, right? So on the east, west, north, and south integrals, all right? But because we're doing time marching, we have to apply a time index of these, right? And so we're going to either supply an n or an n+1, right? And whether we supply an n or an n+1 depends on the time marching scheme that we use, right? So we know that if we supply a time index of n on the diffusion and convection terms, right? And so time index of n means that we're applying an explicit Euler method. Okay. But then if we do n+1, that of course corresponds to implicit Euler. Okay. Right. And so in some ways, this unit right here is kind of a good kind of bow on this entire semester, because we kind of combine a lot of what we've learned, right? And so of course we have our time marching schemes that that you guys just got tested on the midterm, but everything that we've been working on in finite volumes for the second half of the course, we're going to have to go through those derivations as well. Okay. And so same thing with the boundary conditions and everything. Okay. And so I think, since we're so familiar with this process, there's really not much more to say. And so I think the best thing is just to kind of jump into some examples and just see how the derivations work out and see how the code kind of shapes up from here. Okay. Any questions on this? Okay. All right. So let's go ahead and do an example. So I believe we started this last time, but we can just go ahead and pick up where we left off. Okay. And so in this example, we have an explicit Euler scheme for a 1D unsteady diffusion. Okay. So the equation that we have is partial phi partial t is equal to 3 partial squared phi partial x squared. Okay. And so our boundary conditions, we have some unsteady boundary conditions here. And so we have phi of 0 is equal to cosine of pi t. Okay. And we have a Neumann boundary condition on the other side. So our domain is going to go from 0 to 1. And so this is going to be cosine of pi t divided by 2. Okay. And so let's assume a 0 initial condition. Okay. And let's plug in some grid sizes. Okay, so we'll assume a delta x here is going to be 0.2, and delta t we'll assume is 0.001. Okay, so delta t will be about 1 millisecond. Okay. I think I chose this one to be really small just for stability purposes, just so it's stable with code. Okay. All right, so what we're going to do here, just like we usually do, is we're going to take this equation, we're going to derive its time marching equations. Okay. Okay. And so in this case, we have 5 cells, so maybe I didn't say that. Okay. Right, and so we're going to have one time marching equation for each cell. Okay. And then after we derive those equations, we're going to implement its solution in Matlab. Okay. Okay. All right, so we'll take this kind of from the beginning to the end. And so, we're going to start with the differential equation. We're going to apply the finite volume method to it. Then after we apply finite volumes, we're going to apply our explicit Euler. And then from there, we'll work on the equations. Okay, any questions on the problem setup here? Okay. All right, and so let's work on the finite volumes first. And so let's take our equation here. Okay, so we have partial phi, partial t. Okay, is equal to 3 partial squared phi partial x squared. Okay, and just like we normally do with finite volumes, we're going to integrate this. Okay. And we're going to integrate it with respect to dx. Okay. Okay, so let's go ahead and perform these integrations. And so on the left, we have a first order, or we have just regular integral on partial phi partial t. Okay, but we saw how this works out up here, and so I'm just going to go ahead and plug in that expression. Okay, and so this side of the equal sign is going to be phi n plus 1 minus phi n. Both of these are phi sub c. Okay, divided by delta t. And this multiplied by delta x. Okay. Whereas on the right-hand side, right, this integral here is going to cancel out with that. And so what we have is partial phi partial x evaluated on the right side of the cell minus partial phi partial x on the left side. Okay. All right, and so on the next line, I'm going to go ahead and bring down the left-hand side because we're basically done with that. Okay. And on the right, I'm going to plug in our usual linear interpolation, our linear approximation, excuse me. Okay, and so we have 3 partial phi partial x on the right side of the cell, we know is phi sub r. Minus phi sub c divided by delta x. Okay, and then partial phi partial x on the left side is going to be phi sub c minus phi sub l all divided by delta x. Okay. We can go ahead and combine these. And so I'm going to factor out delta x here. And so on the right-hand side, we have 3 divided by delta x. Okay, and this multiplied by phi sub r minus 2 phi sub c minus phi sub l. Okay. And on the left-hand side, we haven't done anything there yet, but let me go ahead and factor out delta t. Okay. Phi c n plus 1 minus phi c at n. Okay. And this is multiplied on the outside by delta x over delta t. Okay. All right, so we're just working through our finite volume method. Okay. So before we move on, we have to look at all the phi terms here on the right. Okay. And we see that these phi terms do not have any time index associated with them. Okay. And so these you need to assign time index. Okay. Oh, yes, plus phi sub. Thank you so much. I'm getting distracted by my iPad's incompetence right now. Keep having to erase stuff. All right. Right. And so since this is a time marching scheme, we have to plug in time indices. And we have two options, right? We have either n or n plus 1. And how we choose that is just based on the time marching scheme that we are implementing. And for this particular problem, we are doing explicit Euler. Okay. And so that means for all of the phi values here that are not part of the time derivative, we're going to apply them at time step n. Okay, so this is going to be phi rn, phi cn, phi ln. Okay. Okay. And so from here, it's just a game of algebra. And so all we have to do from here is just rearrange the terms. Okay. And so what we want to do is that everything that's phi n plus 1, okay, everything with n plus 1, I'm going to put it over to the left-hand side of the equal sign. And everything with n, or source terms, and so source terms as well, is going to go on the right. Okay. Okay, so let me go ahead and multiply both sides by delta t over delta x. Okay, so we do that, we get 3 delta t divided by delta x squared. This is multiplied by phi sub r at n minus 2 phi sub c at n plus phi sub l at n. Okay. And so we can go ahead and multiply that factor through and then move the phi sub c at n over to the right-hand side. Okay. And so if we do that, we get phi sub c n plus 1. Okay, so we isolate that by itself. For the phi sub r term, we have 3. We have 3 delta t divided by delta x squared. Okay, phi sub r to the n. Okay, plus we have a 1. The 1 comes from the phi sub c at n from the left-hand side, plus or minus, excuse me, minus 6 delta t divided by delta x squared. This is phi sub c at n, okay, plus 3 delta t divided by delta x squared, phi sub l at n. Okay. And of course, from here, we can plug in the values for delta t and delta x, and that's going to be our time marching equation. Okay. And so what we can do from here is we can apply this we haven't accounted for boundary conditions yet. And so, this is only going to apply for the interior nodes or interior cells, excuse me. Okay. And so we can apply this to cells. In this case, since we're in 1D, this will be cells 2, 3, and 4. Okay. And then, we can get those equations. And so I'll do that a bit later. But the next thing I want to go over is how to account for the boundary conditions. Okay. All right. But are there any questions on what we've done up to this point to get to here? Okay. Okay. And so this is going to work for cells 2, 3, and 4. But cells 1 and 5, we have to apply our boundary conditions. Okay. And we're going to obtain those modified equations kind of the same way as we've done before. Okay. And so let's start with cell 1. Okay. And so if we go back to the problem statement, we see that cell 1 has a Dirichlet boundary condition on its left edge. Okay. Okay. And so that means, if we go back through our derivation here, okay, that means the value of the derivative here on the left edge, this is going to be modified. Okay. Okay, so it's going to modify the value of partial phi partial x on the left edge. Okay. All right, so let's go ahead and figure out what that is. Okay, so partial phi partial x on the left. Okay. Right. Normally, what we do here is we do phi sub c minus phi sub l divided by delta x. Okay. But of course, we're going to replace this with the Dirichlet boundary condition. So now this is going to be phi sub c minus phi naught. Okay. Phi naught being the Dirichlet boundary condition, and this is all divided by delta x divided by 2. Okay. Okay. For phi naught, that's our Dirichlet value. For this particular problem, we have a time varying function for phi naught. Okay, so this cosine of pi t, this is our phi naught, right? And so we go back down here and we plug that in. We have phi sub c minus cosine of pi t n divided by delta x divided by 2. Okay. And of course, we apply phi sub c here at time step n because we are implicit. Okay. Right, and so now this is our expression for the slope of the solution at the left side. Okay. Okay, so now we can go ahead and plug this guy in. Okay. All right, and so if we plug that in, then what we get is, oops. What we get is phi sub c at n plus 1, right? So that's going to still stay the same, minus phi sub c at n, right? This is equal to 3 delta t divided by delta x squared. Okay. So I've kind of skipped a couple steps, and so I basically multiply both sides by delta t over delta x. Okay. We have phi sub r minus phi sub c. Okay. And so that's standard, and so that's that's the right side slope, and so that doesn't change because we have a right side neighbor. Okay. And then we're going to minus what we have up here. And so what we have up here is 2. The delta x already came out, and so we have 2 times phi sub c at n minus cosine of pi t n. All right. And so let's go ahead and simplify this and rearrange. Okay, and so we do that, we get phi sub c, and so this is for cell 1, right? So let's be clear about that. Okay, so for cell 1 we have phi sub c. Where phi sub c here is phi sub 1, right? So this is phi 1 at n plus 1. This is equal to 3 delta t divided by delta x squared. Okay, multiplied by our right neighbor, and so our right neighbor for phi 1 is going to be phi 2 at n. Okay, plus 1 minus 3 times 3, so that's 9 delta t divided by delta x squared phi 1 at n. Okay, and then we have our Dirichlet boundary condition term. So our Dirichlet boundary condition term here is going to be 6 delta t divided by delta x squared cosine of pi t n. And so that's our time marching equation for cell 1 that takes the Dirichlet boundary condition into account. Okay. All right. Any questions on how we apply that boundary condition there? Okay. All right, so now let's do the same thing for the Neumann boundary condition on the right. Okay. So cell 5. Okay, so this will have a Neumann boundary condition on the right. Okay. And so that means that if we take our derivative here, so partial phi partial x, okay, and we consider the one on the right side of the cell, the right side of cell 5, we're going to replace this directly with our Neumann boundary condition. So we have phi, or gamma of t is equal to cosine of pi over 5, or excuse me, pi over 2 t. Sorry, this just randomly reminded me that I know last week I promised you I would post the finite volume starter code for the project, and I did that, but I did want to talk about it in class, but we're kind of in the middle of something else right now. So remind me, first thing Thursday, we'll talk about the finite volume starter code for the project, because it is slightly different, and so I want to make sure that we go over that in together in class. First thing on Wednesday. I'll try to remember, but if I forget, then just tell me. Okay. Okay. And so if we're going to be replacing this entire derivative here with that expression, then we just kind of carry on just like we did before. Okay. Okay. And so if we do that, we have phi sub c n plus 1 minus phi sub c at n is equal to 3 delta t divided by delta x squared multiplied by, here we have a partial phi partial x on the right, and so this is going to be cosine pi over 2t. Okay. Delta x. Okay. Right. I put the extra delta x there because we're not putting in a derivative, we're putting in the Neumann value. Okay, so when I factor out this delta x squared from the bottom, that Neumann boundary condition term didn't have that delta x, and so we have to include that there. Okay. And then we have minus our usual terms. We have phi sub c minus phi sub l. Parentheses. Okay. And so if we work out the algebra for this, we have phi5 n plus 1, and so that's going to be our term on the left-hand side, right? Then we have 3 delta t divided by delta x squared. Okay. This is multiplied by the left neighbor, and so this is phi4 at n, okay, plus 1 minus 3 delta t divided by delta x squared. Phi sub c here is 5, okay, at n plus 3 delta t divided by delta x, right? Not delta x squared, but just delta x, because that delta x is going to cancel, times cosine pi over 2t. Okay. All right, so now that we have the boundary cells taken care of, we have all the interior cells taken care of, we can go ahead and put all this together into one system, and then see how this is implemented in Matlab. Okay, so let me go ahead and plug in all the numbers. You're probably tired of seeing delta t and delta x, right? So let me go ahead and plug it in, and we're going to obtain the following 5 equations. Okay, so we have equation 1, equation 2, equation 3, equation 4, equation 5. Okay. And so we have phi1 n plus 1 is equal to phi2 n plus 1 is equal to phi3 n plus 1 is equal to okay. And so we have our time advancement equations for all 5 cells. Okay. And so let's do the interior cells first. And so for the interior cells, we have 0.075, and this is going to be the left neighbor. So this is phi1 at n plus 0.85 phi sub c at n plus 0.075 right neighbor, which is phi3 for cell 2. Okay. I'm going to go ahead and repeat that for the other cells. Okay. So those are our 3 interior cells. And so let me go ahead and write the equations for our boundary cells. Okay, so starting with cell 1. And so cell 1 right here is 0.075 V2 at n plus 0.775 V1 at n. And then we have our Dirichlet boundary. So our Dirichlet boundary is 0.15 cosine of pi Tn. Okay. And finally, for our cell 5, which borders the Neumann boundary. So 0.075 V4 at n plus 0.925 V5 at n plus 0.015 cosine of pi over 2 Tn. And so here are our five equations. Okay. All right. And so, of course, you know what comes next, right? And so the next thing is we're going to put this in matrix form. That's just because that's how we do it in Matlab. And so everything with the phi in front, that's going to go into a matrix. I missed a guy. Okay, so everything here will go into the coefficient matrix. They all have a phi in front. Whereas these extra terms will go into like a forcing vector. Okay. And so if we write out this expression, okay, in matrix form, we're going to have phi I n plus 1 is equal to, we use the same colors, A times phi I n plus B. Okay. And so everything circled in purple right there is going to go into our matrix A, and everything circled in red is going to go into our vector B. Okay. And so you can see here, this is our usual explicit Euler form. It's just that we've derived it with finite volumes instead. Okay. All right. Any questions on this before we jump into the Matlab code? Okay. All right. So it's the same. So I mean, it's the same as we've always done, right? And so we kind of just combined our processes. And so we combined our explicit Euler time advancement together with our finite volume method. Okay. And so this was a relatively simple example, just because we have no source term, we have just diffusion. But I think going through a simple example like this, kind of slowly, step by step, will kind of help you illustrate the process. And so you can then apply that same process to more complicated problems, which we'll do after this. Okay. All right, so let's go ahead and look at the Matlab code. And so let me go ahead and share my screen here. Okay. Let's see. This one here. Okay, let me make the font a little bit bigger. It's a little bit too small right now. Okay, so here's our finite volume code. Right? All right, so of course this is posted onto Canvas, and so you can have this for yourself. Okay, but here are all our variables, and so we have the length of the domain is equal to 1, n is equal to 5. That's the number of cells. Okay. We have the grid spacing. We have the value of k. We have dt. Or I guess I chose a different value of dt here. And so I guess I have a time step size of 0.05. We can easily change that. And so if we wanted to match the homework or match the in-class example, we'll change it to 1 millisecond. Okay. We have the values for the centroids of the cells, the number of time steps, and we have A and B. Okay. All right. So all of this is kind of just bookkeeping, just to make sure that we get a video out of this. Okay. And then we're going to start the time stepping loop. Okay. All right, so just as with any kind of time marching scheme, we have a time stepping loop, and so this is going to loop over all of our time steps, and so we have 4 t step is equal to 1 to nt. Okay. And so this is going to loop over all of our time steps, right? So each time step, we're going to advance forward in time by dt. Right? And the next step right here is, you can read the comment here, is that we're going to find the matrix coefficients for all of the interior cells, okay? And so from I is equal to 2 to n minus 1, and so this is going to be just the interior cells. This is what we're going to set as the matrix coefficients, okay? And so for the left neighbor, this left neighbor has a value of k times dt divided by dx squared. And so from the in-class example, this has a value of 0.075, okay? For phi sub c, and so that a at I comma I, this is 1 minus 2 times k times dt divided by dx squared. Okay. And from the in-class example, you can see that this is equal to 0.85. That's what we just computed. Okay. And then we have the right neighbor, which is a at I comma I plus 1. And so that's also k dt over dx squared, which has a value of 0.075. Okay. And so this takes care of everything in A for the interior cells. Okay. So pretty standard stuff, right? And so remember, whenever you have a time stepping scheme, right, you have one outer loop here that loops over time. And then within the time loop, you also have another loop here that visits all of the cells in space, okay? And so of course, we're doing finite volumes, we're not doing finite difference, but the same idea, the same structure is still the same. Okay, so that takes care of all the interior cells. And so now we have to deal with the boundary cells. Okay, so first let's do cell 1, which is a Dirichlet boundary. Okay, and so if you look back into the notes, you can see here that for our first row of the matrix, we have the coefficient for phi sub c. And the coefficient for phi sub c is 1 minus 3k delta t divided by delta x squared. Okay, and so since this is for phi sub c for the first cell, this is going to be a at I comma I, right? Next, we have phi sub r, which is the value for the right neighbor, and so that's k delta t divided by delta x squared. Okay, and then we have the value that's in the vector, right? So this is going to go in the vector b, and so in the vector b we have 2 times k times delta t divided by delta x squared multiplied by the Dirichlet value, which is cosine pi t. And we have the same thing for the Neumann boundary condition. So for the Neumann boundary condition, this is going to take place at cell 5. Okay. And so for the left neighbor, phi sub L, we have a k delta t divided by delta x squared. For phi sub C, we have the coefficient of 1 minus k delta t divided by delta x squared. And then for the right-hand side, for B, we have k delta t divided by delta x times cosine pi over 2 times t. Okay. Right. And so all of these basically do is just they specify the first row of the matrix time advancement situation, and this is specifying the last row. Okay. And so now that we have everything, we can go ahead and time advance. And so remember, sol next right here, that's phi n plus 1. And so if you go back to the very last thing we wrote, this is equal to a times sol cur here being phi sub n plus b. Okay, and then we perform our updates, update the time variable, and all that good stuff. All right, so let me go ahead and run this code. I don't know why I have the number of time steps is 10,000, but we'll see how long this runs. Oh, it's running. All right, and so you can see what's going on, kind of. Okay. It's going really slow. I know why I made the time step size larger, because this just goes really slow. And so you can kind of see it. If you look very closely, you can see the string is kind of wiggling up and down. Okay. So I think I have 2 Matlabs open. So let me go ahead and close this one. Okay. And so this code is working, but it's going really slow because I put the number of time steps to be very large. Okay. But you can see that the string is kind of responding to the changes in the boundary condition, right? And so for the right-hand side here, we have our cosine that's going up and down. And then for the right side, we have our Neumann boundary condition, which is also cosine going up and down. Okay. Let me check and see if it's done. It is not done. let me do this. Let me go ahead and cancel this real quick. Just because I want to show you the result. And so let me go ahead and change this to 1000. And I'll change this time step size to focus. Okay, so of course this is going to change our coefficients, but I want the code to finish. And so okay. So I'll go ahead and change the code. So let me go ahead and run it again. And so you can see the string wiggling a little bit better now, just because we're going a little bit faster. Okay. And so this method was explicit. And so of course, explicit is a lot cheaper than implicit. But if you're running it for 10,000 time steps, that's always going to take quite a bit of time. Okay. And so you can see the string kind of responding there. All right. And so that right there just about covers it. And so that's our 1D finite volumes with explicit Euler. Okay. All right, question. So what does the video represent and how is it applied in real time? Yeah, good question. And so this video here represents the values of phi, okay, as they change with time. Right? It's a little bit hard to see because it's just one continuous string. But what you can imagine is that this string is comprised of 5 different cells, right? And so the different points on the string is phi1, phi2, phi3, phi4, and phi5. Okay. And the video represents how those values of phi are changing with time. Right? So remember, because this is an unsteady situation, the values of phi are going to be changing with time. And so what the video represents is how phi1 is changing, right? And so if you look at just phi1, and I think the video should be done now. So let me go ahead and check the video. Okay. Yes. And so you look at phi1, and so if you just focus on just kind of one point right here, right, you can see that it's kind of oscillating up and down, right? And so that represents that, based on our governing equation here and based on our boundary conditions, our phi1 is going to oscillate kind of up and down. And kind of the trajectory and the path that it takes tells you how the phi is changing with time. Okay? And so, if you want to apply this to your projects, right? In our projects, we're using our phis to represent temperature, right? And so for a case, maybe you're applying like a cyclical temperature, right? And so maybe you're heating this string up and down, heating it up and cooling it down, kind of according to a cosine wave. Then these different values of phi will represent, the temperature of your object as a function of time, right? And so it's going to go up and down, as it reacts to what the boundary condition is telling it to do. All right, any other questions on this before we move on to 2D? Okay. All right, and so that's the 1D case. But of course, we live in a 3-dimensional world, or more importantly, your projects are in 2D. And so let's see how this is applied in 2D. Okay. And also relevant to your project, let's see how we do the time marching in 2D using an implicit Euler. Okay. Okay. All right, so let's take this apart, right? And so we have quite a few kind of advancements here compared to what we just did. Okay? And so first of all, we have implicit. Okay. And so what the implicit means is that all of our convective and diffusive terms, we're going to apply them at time step n+1. Okay. right? So that's different than the previous case. And so in the previous case, we applied a time step of n, okay? And the other thing is that in 2D, right? Okay. Because we're dealing with 2D finite volumes, that means we are going to be dealing with our four edge integrals, okay? Okay. Because remember in 2D, you know, we have a situation like this, right? So we have our square cell and we have our four sides, right? So we have our north side, we have our east side. Whoa. We have our south side. We have our west. Okay. And so remember, each of these four sides here are going to have their integrals. You know, but now we're going to apply our time marching scheme kind of on top of that. Okay. Okay. All right, so let me go ahead and write out the entire expression here. And so, you know, this is going to be for all the integrals, okay? And we'll see how this kind of breaks down and how we apply implicit order. Okay? And so this is going to include, you know, our four edge integrals, but it's also going to include our time derivative term as well as our source. Okay. And so we start with our time derivative term. And so our time derivative term is going to be double integral partial phi partial t dx dy. Okay. Okay. And next we have our four integrals. And so, you know, this is after we apply kind of divergence theorem to split the integrals. Okay. And so we have integral on the east face of phi v dot n hat minus k gradient of phi dot n hat. Okay. This is dy plus, we have our north integral to phi times phi dot n hat dx, or excuse me, yeah, not dx yet. Okay. First we have to subtract k gradient of phi dot n hat. Okay, now dx. Plus, we have our west integral, and so our west integral is integral on the west face, phi dot n hat minus k gradient of phi dot n hat dx or dy. Okay. And we have plus integral on the south, phi v dot n hat minus k gradient of phi dot n hat dx. Okay. And all this is equal to the double integral of our source term. Okay, so we have integral integral q of xy dx dy. Okay. All right, so you probably haven't seen it. You probably haven't seen it in this form in a while, but I wanted to start here just to kind of show you kind of where we're at, right? Because remember, the finite volume scheme, the way that we interpret it is that we take integrals of our governing equations, and this is kind of right after we applied our divergence theorem. Okay, and so it's been a while since we've seen this, but you have seen this. Okay. And so we saw this kind of when we did convection for finite volumes. And so the only addition here is, of course, our time derivative term. Okay, so that's the only thing that's going to change. But of course, that one small addition is going to result in a lot of changes in how we approach this problem. Okay. Okay. And so if we kind of work on this for a bit, okay, and so we basically perform all the dot products, and so we perform the dot products with the n hats. Okay. We also apply our trapezoidal rule. Okay. Remember, the trapezoidal rule lets us evaluate the integrals without actually integrating them. Okay. We do that, and we end up with the following. Okay. All right. So first, we have the time derivative term, and so we have partial phi, partial t. Okay. We evaluate this at the centroid. And then we evaluate the integral using trapezoidal rule. And so that becomes just delta x, delta y. Okay. Plus. Then we have everything on the east integral. So we have phi sub little e times u minus k. Partial phi partial x on the east side, delta y. Okay. Plus. Same thing on the north, and so we have phi sub little n multiplied by v minus k. Okay, minus k partial phi partial y, evaluate on the north side, delta x. Okay, minus. Okay. We have that minus sign out in front because of the normal vector, right? So remember, the normal vector on the west side is -1. We have the same thing on the south. Okay. Okay. And all this is equal to the source term, which is q at xc, yc, delta x, delta y. Okay. All right. Okay. So it's a lot of terms, but we're still not quite there. Okay, because the next step that we're going to do is we're going to take all the edge values. Okay, so all of the terms with the little letters, and plug in their cell-centered approximations. Okay. The other thing we're going to do here is we're going to plug in our forward difference for the time derivative. And let's just stick with that for now. So we're not doing kind of too much at once. Okay, so let's go ahead and plug this in. Okay, and so first we have the forward difference for the time derivative. And so instead of partial phi partial t, we have phi sub c n plus 1 minus phi sub c at n, all divided by delta t, okay, multiplied by delta x, delta y. Okay. Then we have the self-centered approximations, right? And so first we have phi sub little e, okay? And for now, I'm just going to assume kind of a low order central scheme, okay? And so for phi sub little e, what we say is that this is equal to phi sub big E plus phi sub c divided by 2, right? And so that's our usual approximation, right? And so our face value is just simply the average of the two neighboring cells, okay? Minus k phi sub big E minus phi sub c, all divided by delta x. Okay. And multiply this by delta y. Okay. And we're going to do the same kind of approximations for all the other cells. Okay. And so next we have the north. And so on the north side, we have v phi sub big N plus phi sub c divided by 2 minus k phi sub c minus phi sub big N divided by delta y. Okay. Everything multiplied by delta x. Okay. We have the same thing for w, and so we have minus u phi sub c plus phi sub w divided by 2 minus k phi sub c minus phi sub w divided by delta x. Okay. And all this is multiplied by delta y. Okay. And finally, we have the same for phi sub south. And so for phi sub south, we have a minus v phi sub s plus phi sub c divided by 2 minus k phi sub c minus phi sub s divided by delta y, all multiplied by delta x. Okay. Okay, and then all that equals the source term q at xc yc times delta x delta y. Okay. All right. So we're going through the entire finite volume derivation, right? But I want to show you these steps again. You know, I know we've seen this before, and I know it's tedious, you know, writing out all these terms, you know. But I want to make sure I kind of expose you to this again, just so that when you go to do this for your projects, you kind of know what you're doing. Okay. The only difference for your project is that instead of doing the simple central scheme for the convection terms, right? And so for the term that's in front of you, you would plug in the quick scheme instead. Okay. But you would run through this exact same exercise. Okay. And so, of course, you know, we're not quite ready to move on to the next step, because in the next step, you know, before we move on to the next step, we have to apply a time index to all the convection and diffusion terms. Okay. And since we are doing an implicit Euler scheme, that means we're going to apply a time step of n plus 1 to everything that doesn't have one yet. Okay. And so for phi sub e, this is going to be n plus 1, plus 1, n plus 1, n plus 1, n plus 1, n plus 1. You guys get the point. And unfortunately, it's a lot of terms to write it on. Okay, so I think that's it. Okay. All right, so now that all the phi terms, you know, we don't have any derivatives anymore. We don't have any more edge values, right? we're getting close because all the phi terms here, those are in terms of self-centered values, and every phi has a time index associated with it. Okay. Now it's just cleanup, and so now it's just kind of algebra from here. So it's been a ton of algebra, but just a few more algebra steps. Okay. And so what we're going to do is that we're going to move everything that's phi n plus 1 to the left. Okay. And then to the right of the equal sign, we're going to move everything that's phi n, okay, plus q. Okay. And so if you do that, of course, I'm skipping all the algebraic steps, but I want to make sure I finish a bit early today, just so I can have time to pass out the exams. Okay. But let me go ahead and skip to the result. And so this is the result of what we're going to plug in terms of coefficients in the Matlab code. Okay. And so in the end, what we get is u delta t divided by 2 delta, right? Where delta here is the same as delta x and delta y. Okay, remember, we're assuming an even grid spacing. Minus k delta t divided by delta squared. This is phi sub e n plus 1. Okay. Plus v delta t divided by 2 delta minus k delta t divided by delta squared v sub n at n plus 1, okay, plus minus u delta t divided by 2 delta minus k delta t over delta squared v sub w n plus 1, okay, plus minus v delta t divided by 2 delta minus k delta t divided by delta squared v sub s n plus 1, okay. And then we have the coefficient for phi sub c, and so that's 1 plus 4k delta t divided by delta squared, okay. Phi sub c n plus 1. Okay, so that's the hard part, and so that's everything on the left-hand side. We end up with a lot more because this is implicit Euler, right? And this is equal to q x sub c y sub c, okay, delta t plus phi sub c at n. And so this monstrosity right here, probably the longest equation or longest relationship that we'll have in this class. This is our time advancement equation for implicit Euler and 2D convection diffusion. Okay? Okay. So of course, this is only applicable to the interior cells because, of course, this relies on the fact that we have neighbors on all 4 sides. And so we'll talk about boundary conditions next time. Okay. And then next time we'll see it applied into a problem as well. Okay. And just like we did today, we're going to go through the problem. We're going to go through its MATLAB implementation, just so that you're prepared for that. Any final questions before we wrap it up for today? Okay, all right. And so if you're here in person, you can come pick up your exam. If you're online, you can come to my office and pick up the exam if you're going to be available. Or I'll bring it back on Wednesday as well if you can free to pick it up. Okay. All right. So thank you everyone for tuning in today. Hope you guys enjoy the rest of your evening, and I'll see you guys on Wednesday. Thanks, guys. So the exams will say out of 50 on there, but then online it'll be out of 45.